In this paper, we introduce a novel approach to enhancing model performance and efficiency through the use of parameter-efficient fine-tuning, PEFT, on tasks of interest. Our method, which we refer to as lmttPHATGOOSE, leverages the low-rank adaptation, LoRA, technique, incorporating trainable modules such as pairs of trainable matrices at every linear layer of the model. This approach significantly reduces both computational and communication costs, thereby facilitating easier participation and contribution from various contributors. Following the initial training of PEFT modules on their respective datasets, contributors further refine these modules by adding a sigmoid gate layer in front of each PEFT module. This gate layer is then trained for a relatively short period, using the same dataset and objectives as the initial PEFT training. This step enables the gate to effectively determine the necessity of activating the PEFT module for a given input, enhancing the model's efficiency and adaptability. The collaborative aspect of our method comes into play when contributors share their trained PEFT modules and gate vectors. We utilize these shared resources to construct routers from the trained gating vectors, enabling top K routing during inference. This routing strategy significantly improves zero-shot generalization capabilities by selecting the most relevant PEFT modules for a given input, as opposed to relying on a single expert model for all inputs. During the inference phase, our model, lmttPHATGOOSE, calculates the affinity between PEFT modules and input activations. It then assembles the top K PEFT modules for each activation and computes scaling weights for each module. This sophisticated routing mechanism allows the model to adaptively select the most appropriate modules for each input, solely based on the information contained within that input, thereby enhancing performance on unseen tasks. Overall, our lmttPHATGOOSE method successfully recycles PEFT modules from various contributors to significantly improve zero-shot generalization capabilities. This is achieved without necessitating extensive additional work or access to the contributors' datasets. Our approach supports the hypothesis that learning a per-token and per-module routing strategy can outperform traditional routing strategies that rely on a single expert model for all tokens, thereby advancing the field of efficient and adaptive model training.